Okay. Yeah, I don't know where I got lost, but anyway. So yeah, so priority queues, to maintain these priorities or support extracting the element or item with the lowest key value, heap look like very natural candidates. So you must have seen implementation of priority queues, say for example with arrays or linked lists, where it so happens that the worst case complexity of operations like deleting an element from the queue could take order of n time. Okay. Whereas, I mean, priority queue, when you don't have priority, then of course you can do it in constant number of time, constant amount of time. So, so this property of heap, so where insertion can be done in order of log n time, minimum can be seen in theta of 1 time. You can remove the item with the minimum value, key value. You can imagine as priority, that is highest priority, can be done in order of log n time. So this kind of, sometimes you also need this decrease key operation. So these are kind of useful in implementing priority queue. Okay. So it's essentially, I mean, you can see that, so these operations of priority queue, so given an element, insert with some key value, it does have a key value. So you return the max in the case of max priority queue. In the case of min priority queue, you return the minimum. Okay. You might also want to remove the element with the minimum key value. And also you might have decrease key operation. Okay. That is, given an item, you change the value of the item to k. Okay. So the term decrease means you will always increase the priority. Okay. I think in the last lecture itself, one of you were asking, okay, so why decrease key? I mean, with isn't just change keys of, I mean, isn't it better to implement that? Well, so contextually, I mean, usually, at least in the applications, say for in the case of priority queue, you will always be making a process with higher priority. Okay, but the procedures can also be modified to change the value of the key rather than to decrease the value. In the case of max priority queue, we call it as increase key. So it's just been traditional. That is all. Okay, the procedure can be modified to also accommodate that. But in most of the applications, this is what is required. Okay. So you can see that each of these operations, now inserting an element. So if you just, the idea is to maintain, let's call this as priority queue, as a heap, as a min heap, with respect to the key values. Okay. So if you do this, you can see that each of these operations can be done in order of log n time. So order of log n time, order of log n time, order of log n time. So whereas this is basically getting the value from the root, so we always assume that the root of the heap is the first element. That's pretty straightforward to do that, and it can be done in order of 1 operations. Okay. So all we need to know is we can implement priority queues using heaps, a straightforward implementation. There is nothing more. So one of the reasons why we even consider decrease key or increase key in a heap was basically to implement priority queues. Okay. So usually priority queues are the ones which require increase or decrease key operations. Yeah, so all other operations, I mean, they are also useful for heaps as such. Okay. So this is what we are going to assume now. So we assume that we can implement priority queue. I'll use the term only priority queue now onwards, no min there. So assume that the element with the minimum least key has the highest priority. Okay. We'll see how to implement Prim's algorithm. That's our main purpose here. Okay. If there are any questions, I'll pause for a minute. I hope I'm not logged out. Just a minute.
Hello,
Yes,
sir. Can you give us a use case of the decrease key operation?
we will be seeing it. So I mean, you can just imagine if you want to increase the priority of certain item, right? Okay, so in this
Yeah.
case, if you want to increase the priority, say item A you should want to increase the priority, say priority to 1.5. So then you can use decrease key. So we'll see that while we implement Prim's algorithm. Okay.
Okay, sir.
Yeah. See, for example, I think many scheduling algorithms in operating systems, right? They kind of use this priority queue and scheduling or even resource allocation algorithms. Okay, so where each process will be allocated a priority. Even I mean, if you look at a Linux system, right? In the Linux system, processes have priorities, right? So there is this nice command, right, which actually allows you to allocate a priority. Okay, so while scheduling, those will be scheduled with the priority basis. Okay, so usually these implementations there again use priority queues. Okay, so to maintain the priorities. I'm not sure if most of the operating systems use Heap. I believe so because it's far efficient. Okay, so we'll go to Prim's algorithm, implementation of Prim's algorithm. Okay, so the main step that needs to be implemented is this. Okay, so you at every point of time, so what you have is like a partial tree built. Okay, so at the beginning you can assume node 1, and at every point of time you have a partial tree, so you want an outgoing edge out of that tree. Okay, I mean, when I say tree, partial tree of a subset of nodes, say S is that subset, you want an edge of minimum weight going out of it. Okay, so how do we compute it? So in the naive implementation that we discussed 2 lectures ago, it was if you have adjacency matrix, what you do is you just imagine intuitively, you just imagine this as one node. Okay, so you basically so whenever you add a node to S, so what you do is you contract this node, these nodes into single. Okay, so all you need to do is you need to merge the adjacency matrix row corresponding to V with that of S, assuming that S is like a single node. Okay, and you need to compute minimum at every point of time. I mean, minimum for the resulting adjacency matrix. Okay, or adjacency list, what you call as. So that will take order of n time per iteration. So overall, it will be order of n square time. Okay, so we want, so let's just imagine. So one way to do this would be you order. So see, first thing is, well, we are going to use heaps, or in fact priority queues to implement this. Okay, but what do we store in the heap? What should we store in the heap? So what we want is yeah, please go ahead.
Is this of the graph?
So that's a natural candidate, right? So it is natural to store edges of the graph. Okay, because so what we want is a minimum weight edge here, right? Only thing is it has to satisfy property, certain property. So one way to do it is, so you maintain, so first implementation, okay, sorry, I thought I had a blank state. Okay, fine. So first implementation, just go one page up. First implementation is the following. Okay. Use a heap to store edges. Okay. So we'll have a min heap with weight as the key. Okay. So your heap, I'll draw it as a tree now, has edges. Okay. So E1, E2, E3, and so on. Only thing is, this is a minimum weightage. Okay. Now let's try to see the complexity of implementation. So how will you manage this? Okay. So first thing is, so we may have to compromise a bit. Okay. So when you start with the vertex 1, what is the minimum weight edge that you want? The minimum weight edge that is incident on 1, right? Yeah. Isn't that right? So what I'll do is I'll compromise a bit. I'll not say that, okay, we'll start with one vertex. Okay. So we'll take the first minimum weightage to begin with, only the first step. The first step will look like crucicles though. Okay. Yeah. So the first step, take the minimum weightage. Take the minimum weightage. Using extract min. Okay, I'm audible, right?
Yes.
Okay, okay. Yeah, so after that I am a bit scared every time. Okay, so extract min. Okay, so what we do is, so say E1 is UV, then we set S as UV. Okay, T as E1. Okay, this is my partial tree. That's the only modification I do, so that I mean, see, nothing, no big deal here. But anyway, so that the implementation is simple. Okay. Now, what is the update to the heap that we need to do at this stage?
Extract
just
this min and then restore the min heap property.
That is all right. So that extract min takes care of, right? So extract min and then heapify. That's all, right? Then min heapify. Okay. So now let's consider a scenario. So let's say we have some graph here, some example graph. Okay. So this was the minimum weightage 1. Okay. So all these are edges are in the heap. Okay. So 2, 3, 1, 4, 2, 3, 3. Let's say. Okay. So this vertex is 1, 2, 3, 4, 5, 6. Okay. So my S is 1, 2 now. Okay. T is 1, 2. Okay. So now what is it we want to do? So we want to extract min, right? But if I do extract min, I will get this edge, right? So what will I do? but I want either this edge or this edge. So min of them, that should be this, right? So you see a problem with the implementation, right? I'll end up running Kruskal's algorithm rather. If I do extract min, I'm going to get to this edge. That's basically Kruskal's algorithm. But what I needed was these edges, right? So with the first implementation, there is a problem. You cannot really implement it right away. So you need something else. You need some other value there, right? So you also probably need priorities. Okay, so you will need priorities to these values. Okay, so what I want is, so I want min among these. So that means these should have the highest priority. Okay, yeah. So one, say after I grow the tree, so let me mark as red edges. Okay, so this is my second step according to Prim's algorithm. Okay, now what are the edges should be having highest priority? It is these edges, in fact including these edges. Okay, so they should have the priority, highest priority, and they should be, so I should be getting minimum weight edge among these. Okay, so once I include this edge, then what are the edges that have the highest priority? It is these edges. So this should be excluded. So when you include the least weight, this edge, then it should be only these which have the highest priority. So one of the edges should be returned. Okay. So directly storing the edges in the heap will not work. Okay. So you'll have to do some modifications. Okay. So the modifications is you may have to give priorities. So priority, so how do we maintain these priorities? That is something that we are going to discuss. So what are the priorities and so on. But one thing is, so one idea that while you can implement it with storing edges, so what we'll do is we'll store vertices instead. Okay. The heap will be storing vertices. Heap or priority queue. We'll be actually calling it as priority queue. We'll be storing vertices rather than edges. Okay. And we'll be assigning priorities accordingly. And yeah, so I'll discuss about priorities. Okay. So maybe I'll demonstrate with our example. Okay. So it is here. Okay. So I'll demonstrate with this example that we used earlier. Okay. So how to maintain that. Okay. So let's go back to our original Prim's algorithm where we are not picking the least weight edge first up. Okay. So we are starting with vertex number 1, let's say. Okay. So let's just imagine what are the informations that we need to store about 1 for the first step. What is it we need about node 1? The minimum weight edge incident on it, right? If the weights are repeating, all minimum weight edges, right? So the information that we need is weight of the minimum weight edge. Okay. So let's see. So what we need to store? Weight of min weight edge out of 1, as well as the edge, we need to know the edge, right? So the information that we need is, so which is the neighbor of 1 with the least weight. So this is equivalent to saying neighbor of 1 least weight. Okay. So for this, what we do is, so we'll use priorities. Okay. So we'll use priorities so that we get this information. Okay. So what we do is initially we assign priorities. So in green, I'm going to write the priorities. Okay. So every node will have a priority of infinity. That means everybody has equal priority. That means I won't be starting with the first node. I'll be starting with any of the nodes. Okay. That is one modification that we do to the stated Prim's algorithm. Okay. So what we do is initially set priority to every node as infinity. Okay. So one thing to note is in Prim's algorithm, it really does not matter where do we start from. Where do we start from? Okay. It can be that node 1 or node 2, node 3, anything. Okay. So it really does not matter where I start from. So what we do is, so with these priorities, so store all vertices in the heap, or let's call it as priority queue. With this priority, with infinity as priority. That means some largest number, okay, larger than any of the edge weights. Okay. So instead of starting with 1, so what we do is first step 1. So VB, say Q be the Q, okay. Extract min. Sorry. Min Q. Okay. So now what we do is, so we need to assign, so assume that the priority, lower the priority value, the higher the priority. Okay. That means element with the minimum priority or minimum key value has the highest priority. Okay. So what we do is we just stand here, say for now, let's assume that V is 1. Okay. So let's assume that V is 1. Let's assume that V is 1 for our sake. Okay. Now you just look around. Okay. For each of the neighbor of 1, we update their priority. Okay. So any thought what should be their priority? So the idea is our next extract min should give me the cheapest neighbor from 1. That is the minimum weight neighbor incident on vertex number 1. I'm assuming that V is 1. Okay. In general, it could be any of the vertices and it really does not matter. So what we did is initially we assigned priority as infinity for every node. We stored all of them in the priority queue. Okay, basically as a heap. Okay, we are using a heap implementation of the priority queue. So the first node that we have is V. We just apply extract min. Okay, so the minimum weight, minimum priority vertex is extracted. Okay. Now what we do is we look at its neighbors. There are 4 neighbors, right? 3, 13, 14, and 4. Okay. So for each of the neighbor, we update the priority. So what is the priority there? Initially it was infinity. Now it is the minimum weight edge out of 1 to that node. Okay. I mean, we don't have a multi-graph, so there is only one edge. So it's basically weight of that edge. Okay. So what we do is, for every U such that UV is in E, decrease key, U, weight of UV. Okay. Now what happened? So let's just imagine this was node 1. These are other nodes. Okay. So all of them have priority infinity now. Okay. Key values are all priority infinity. So what you did is after step 1, you have changed the root node. It is no more 1, it's some other node. But what did you do? So for every neighbor of 1, okay, you updated its priority. So all of them had infinity as a priority. So every neighbor, so let's say nodes 3 was here, 4 was here, and this is, let's say, 13 and 14. Let's say 14 was here. Okay. So increase their keys, you decrease their keys according to their weights. So now key of node 3 will be 1. Now node 4 will be, what is the weight? Not 3, right? 3 or 2. Okay. 2. What is for 13? It is 3. 14, it was 8, right? 3 and 8. Okay. This is how it is. Now you apply heapify. I mean, when you apply decrease key, you also apply heapify along the way. Okay. So this will be converted into heap. So heapify. This will be converted into heap. So what you will have is 3 here with 1 as a priority and other whatever. Okay. Some of them will be with infinite priority and so on. Okay. Now if we apply extract min, what will happen? Step 2, WB extract min. What will we get? Yeah, can somebody respond? Sorry?
3 will be extracted, sir.
3, right? So 3 is what we are going to get. Yeah. So what is that 3? 3 is the least weight edge incident, I mean, least weight neighbor incident on 1, right? So what we get is 3. Okay. So we get 3. That means we add this to the edge. So add now set T is T union. It was empty set initially, UV. Oh, sorry, WB, sorry. Or VW, whatever. Order does not matter. Okay. You add this edge, the corresponding edge. So what is the update that we need to do? Can somebody think about it? Can somebody tell me?
So edges incident on W, we need to add them as well now.
So now you need to consider the edges incident on W, right? Okay. But how do you update? So what is the update that you would do?
Yeah, decreasing the priority by the weight of the edges.
Yeah. So you just look at the edges incident on W, okay, and look at the corresponding vertices. They already have some priorities, right? So this guy still has infinity. So after the second step, what was the priority? So priority of 4 was, after the first step, priority of 4 was, did we take 2? We took 2, right? So 2, okay. Now, does it have a neighbor with 3? It does not. So its priority will not change. 2, so this node 2 will have priority of 2 now, okay. This node 13, will its priority change? Its priority was 3 already, right? It will not change. So always, so let's just imagine, say this was, instead of 4, let's say this was 2, okay. So in that case, the priority of 13 will change to 2 now, okay. Priority of 2 will change to 2 from infinity. Yeah, is that clear what we are doing? We are basically doing the same kind of contraction operation, okay. So what we are doing is, so initially everybody has infinity as the priority, okay. Once we pick a vertex, all its neighbors will have changed priority, definite values, which is not infinity, which is basically the edge incident on it. Once we grow, so once we extract min, what we get is a minimum weight edge which is incident on that vertex 1, which is v, which is the first outcome of extract min, okay. So once we do that, what we do is we do a local updation. So all neighbors of this, so we'll get an update, okay. So what you do is you look at their priority. If its priority is infinity, you change it to this value. Or if the new edge weight, so that is edge incident on this new vertex that we have added, we called it as W here. Where is that? Yeah, W. Okay. So W here. So if weight of W to say U is smaller than its priority, then you update the priority. Otherwise, don't change. Okay. So in this case, so if it were 4 as before, then it won't change. Okay. If it was 4, then it won't change for vertex 13. Else it will change to the edge weight of 3 to 13. Okay. So this way you proceed. Now you apply extract min again. So one of the edges will come out, either this or this. So let's say this came out. Okay. So now what you do is you look at neighbors of 4, update their priority. So priority of 2 was 2 already after this extract min. I mean, after this adding this edge and updating accordingly. Now the priority given by 4 is 4, will not change. But 5 had infinity, so you update it to 6. 6 had infinity, you update it to 2. 9 had infinity, you update it to 1. 12 had infinity, you update it to whatever value. So I believe I'll take it as 2. Okay, that way. So all you do is whatever vertex added, all its neighbor, you update the key. You basically decrease key. We call it as decrease key because initially everything was set to infinity. Okay, so you will update the key only if the key value is being decreased. Otherwise, you will not update. Okay, so that means you are giving higher priority. So at any point of time, our priority queue, what we will have is, if you have T as a partial tree, it will have a heap where non-infinity weights are only, that is non-infinity priorities are only to vertices which are having at least one edge to the partial tree that I have. Okay, and if you apply extract min, what you get is the minimum weight edge. So that exactly what we want here. Okay, so minimum weight edge with this property. That is a play with priority. Okay, so you set, so what we did is for all other edges or all other non-relevant vertices, we set the priority as infinity. And these vertices no more reside in the queue. The vertices which are in the tree no more reside in the queue. They are out of the queue. Okay. Yeah. So I'll wait for a minute if you have questions before I describe this formally. Okay.
Hello.
Yes.
Sir, so after we update the edges, like after
Yes.
we have a vertex and then we update the edges, you said we do the heapify thing to reconstruct the heap.
Yeah, so what we do is, I mean, see, at every decrease key, you'll have to do heapify, okay? Otherwise, heapify will become expensive. Okay,
Okay,
so
okay. Now,
yeah, after every decrease key you'll have to, because otherwise you can see it here itself, right? If I apply heapify at once, it's going to be troublesome. I would apply for each of them, right? So it's better as soon as you decrease key, you heapify. As soon as you decrease key here, you heapify, and so on. Okay, so this has
okay,
to be done together. Yeah,
okay, sir. Okay.
yeah. So, okay, are there any further questions? Okay, so one more data you need to store, right, along with the priority. Say this was my partial tree I have built. Okay, now when I apply extract min, so I would be getting say 9, which has weight 1. Okay, so this is the one I am going to get. Now when I get 9, don't I need to know which is the edge I need to include in the tree? 9 4 is what I have to include, right? My set of vertices already was 1 3 and 4. Okay, so the edge could have been from 9 to 1 or 9 to 3 or 9 to 4, right? So I'll also need this information. So which is that neighbor which minimizes the edge from that vertex to my current tree? Yeah, so I'll also need to store that information along with the priorities. So each of these nodes will also have to store the neighbor information, that is, which is the edge which minimizes the weight. Yeah, so our implementation is basically also taking into consideration that. Okay, so what we do is, so for every node we'll also store, let's call this as nb, so v dot nb. Okay, so yeah, so the basic implementation is this. So the step 2 of the algorithm, we replace it by this procedure. So initially we initialize the priority queue as with infinity priorities. I mean priority as infinity or key as infinity for every element. You apply v as extract min, and you assume that you have another attribute, let's call it as nb or neighbor for that. Okay, so every node will store its neighbor. So every node with priority as not infinity will have a neighbor. Okay, priority as infinity, you can just assume neighbor as nil. Okay, so here after having these two edges, so 9 will have neighbor as 4, 5 will have neighbor as 4, 6 will have neighbor as 4, and 13 will have neighbor as 1. Yeah, 2 will have as neighbor 4. Okay, that's it. So that information has to be there. So 3.nb, sorry, 2.nb will be 3, 13.nb will be 1, and so on. Okay, so yeah, so this is kind of summary of what we do. So I'll give the full algorithm probably in the next lecture. What is the time now? Yeah, 54. Okay, so I'll not continue further. So just look at this demonstration and just convince yourself that you understand. Okay, so in the next lecture we'll give the full detailed analysis. We'll give the full algorithm as well as detailed analysis. Okay.
hello.
Yeah.
Sir, so you are saying that for every vertex in the current tree, we are storing the minimum weight neighbor also.
Yeah, that information is required, right? Otherwise you can't build the tree. You wouldn't know which vertex, right? Which is the edge that minimizes the weight. That edge
So,
has to be added to the tree, right?
so sir, it's a bit confusing for me now because
Mhm.
extract min, we are storing vertices in the
heap, we are doing extract min to get the
Yeah.
minimum weight edge
Yeah.
from that heap.
Minimum
And
key edge. Minimum key edge. Yeah.
okay, the minimum key edge from that.
Yeah. So you can imagine each node is a structure, right? Structure. It also stores the neighbor information. That's
No, no,
fine, right?
not that, not that.
Mm-hmm.
The thing that is
Mm-hmm.
confusing me is we are going through the neighbors of each and every vertex which are currently in our tree,
Yes.
and that neighbors are only the minimum weight neighbor, minimum edge weight neighbors.
Yes. Yes.
Okay. From that, we are doing the min heap, min extract.
So yeah, what we do is see, we are storing the nodes, right? So all of the nodes are in the tree. Okay, so initially all n nodes. So but suppose we have built tree for 3 nodes, that means n minus 3 nodes will be in the tree. Priority will be less than infinity only those which are neighbors of these 3 nodes. Okay, which have at least one of these as neighbors. Now, what are the priority values? The priority values are basically minimum weight among these edges. So that means for 9, you look at these 3 nodes, look at these edges, which one of them is the minimum weight. So the weight of that will be the priority. But that,
So,
yeah,
but are we checking for cycles here?
there is no question of cycles at all, right?
No, since suppose if there is at suppose vertex 9, the
Mm-hmm.
minimum edge weight is with 1 only, that vertex 1.
That is fine, right? You can add that.
Okay, okay, it's
It
okay.
won't create cycle, right? Because the
No,
way
no, not
we,
that one. I thought 4 9 is also included. Suppose from 4 we have an edge to vertex 3.
no, that is not right. So once we add this, so when we say extract min, that vertex is gone out of the picture, right? It's out of the heap. So Girija, can you stop the recording? Yeah.